So first of all, I apologize for not being able to make it there in person. I know it's just Madison, but I was flying back into O'Hare this afternoon, and that went about as well as you can imagine. So 3 hours late back to Champaign, and I figured I'd do this on Zoom. So you've heard things like 10 million alerts per night. And this is the source of those 10 million alerts per night. This is the Vera C. Rubin Observatory, and it's going to be beginning the legacy survey of space and time in essentially a few weeks at this point. And this is where you get the rate of those alerts that you've been hearing from Michael, Wade, etc. Now, I am not going to focus on the science like the speakers before me. I was asked by the organizers to talk about the compute bottlenecks, which was perfect because I don't have solutions to most of the bottlenecks, but I can tell you where the problems are. Um, and actually, the biggest headline is I don't think the problem is actually the rate. 10 million alerts per night is not a shockingly high amount of things. And if you focus on the computing bottleneck that you have with time domain and multi-passenger astrophysics, rather than the scientific challenges, you can actually identify a few real computing issues that affect you regardless of who you are. But I'm going to speak with about four different hats on. One is if I was one of these broker systems between Rubin and end users, in which case I think the issue is really that you have streaming compute, but you actually have a very hard tail that you have to do with your latency and chop it off to get anything useful. If you are in a science collaboration like the dark energy science collaboration, which I'm the spokesperson for, then your challenges is not just one data set and real-time streaming alerts. You can give up real-time streaming alerts to do the thing that we had just talked about, try to find type 1a cosmology. But now you're trying to do cross-archive data assembly. There's no common key to search across these archives. And you actually have to deal with this over 10 years. So you've got a massive provenance tracking problem. If, like Michael or Shreya, you care about multi-messenger astrophysics, then as they mentioned, you're trying to do real-time optimization. You have real hard deadlines. You have to take the observations before the event fades away or before the field sets below the horizon that night. But the bigger challenge, I think, is multi-facility orchestration. You actually have to tell a different facility to go off and do the observations and get their data back into your system to know that it has happened. And then if you are trying to do this all with AI and you've got this mode of operation where you have grant funded batch HPC, it's a really terrible model because the sort of things that Wade is building, these Oracle 2 Omni systems that are great for running on GPUs, they need inference running 24/7 in the cloud for 10 years. And I don't know how to fund them with a CSSI award that's like 2 to 3 years long. Each of these bottlenecks in reality actually affects every single science case, but I'm going to pretend this problem is separable. And I'm also going to pretend that human RSCs are just not a problem that we'll consider because it's actually a funding issue, not a computing issue. But they are essential, as we had mentioned. So if I take the broker perspective, what a broker does is really sit between something like Rubin and a whole bunch of end users. Now, nobody actually wants 10 million alerts per night. No individual user cares about all of that. Brokers were supposed to be really a piece of middleware between Rubin and the users. And the game that they were playing was essentially that they would be processing the full stream of alerts, filtering those alerts to users based on the user's own science interest. Rubin has a certain amount of bandwidth out of the US data facility, and that was enough to stream all of the alerts to 7 separate broker systems. And 0 out of 7 have funding to even operate for 3 years at this point, as far as I know. So the bottlenecks that you actually have with brokers is the brokers don't know a priori which of those 10 million alerts per night is interesting to which user. So they, regardless of what you want to do with the alerts downstream, they have to process everything anyway. The second issue that you have is that each user has a different science interest. You just heard from Wei that he cares about superluminous supernova, these things that occur in dwarf galaxies and are very bright and go on for months potentially, versus the kilonovae, which are a few days long and occur in a different kind of galaxy. And so you either have to do processing that's very generic and compute something that everybody can use, or you've got to run people's own algorithms, things like this Oracle 2 Omni, on your own compute. In which case, you've got a DevOps nightmare. You were essentially saying, yeah, I'll take your code and run it on my computer systems. And you all know how hard that is. The third issue is that Rubin sends out all of its alerts roughly 60 seconds after the shutter closes. Not really this early right now, but sooner or later it's going to get to that number. And you've got to batch process all of your alerts within that window. The number of alerts per batch also can vary by a factor of 100 because if you're in the plane of the galaxy, you've got way more sources than if you are off looking in the galactic halo. So you're going to need elastic compute for all of this. And the other issue is that every user has this different requirement for how much of the history of each event they want. If you care about something like changing look AGN or tidal disruption events in the course of galaxy, maybe you want a light curve that is several years long versus someone like Shreya who wants a kilonova light curve that is, 4 to 6 Rubin epochs. So you've got a massive database design issue here. I'm not going to tell you bottlenecks without also giving you partial solutions to these problems, but I don't claim that they're good solutions. And my solution for, well, how do we actually handle this much data over time is just to hope that computing keeps getting cheaper. How do you limit how many filters a user can run? I think what brokers are trying to do right now is limit the number of power users to the LSST science collaborations and actually have more generic and cheap quantities that everybody else can use. So maybe one Oracle to Omni, and then everybody else gets the sort of light curve features that you heard mentioned in, say, Michael's talk. This isn't great, and people with resources, groups with resources, the Caltechs, the Harvards, the Princetons of the world, that can do downstream compute, they will have a strong advantage in this. Now, I also think there's a role for AI in here, and I think people like myself are working on these foundation model latent spaces and agentic AI that we can give to users as a downstream longer solution. But as Ved said, this is not ready yet. The hard tail latency of how to deal with all of this compute within 60 seconds and let's move on, I don't actually have a good idea how to fix this long term. For now, we're okay. In 3 years of Rubin, when it really ramps up, I am not sure how we deal with this. And for the database issues, well, right now people are using a combination of NoSQL approaches. So you see MongoDB, you see Cassandra, Antares, the one broker I work on, uses Google Bigtable. But this is all already breaking down. So Rubin's own alert production database has had issues in early commissioning with the deep drilling fields because it's taking too many visits in the same areas in those regions over and over to be able to retrieve all of them quickly enough. So we've tested these all, of course, only with simulated streams and with ZTF, but we've never been able to do a full Rubin scale test because there just isn't the money for that. So when people say, can we replay previous alerts through the brokers? Well, if you had 10 times the amount of compute, maybe we could. So I can also take a different perspective. I can take the perspective of something like the Dark Energy Science collaboration and just say I'm going to relax the real-time aspect. I don't care about streaming data. I'm going to simply care about getting the data from Rubin each data release, and I'm going to deal with that higher latency. And that's okay for an experiment like the Dark Energy Science collaboration, where our goal is to understand dark energy and dark matter. We use things like type 1a supernovae. We use these binary neutron star mergers with or without their electromagnetic counterparts. You heard about standard sirens. And we try to do things like build a Hubble diagram. Now, I don't need to find those supernovae in real time. I can identify them well enough photometrically so can live without most of the spectra or get some that are serendipitous. And you might say, well, this avoids the problem, right? I'm not dealing with real-time streaming data. I don't have to have all of that complicated infrastructure. But I can show you the pipeline diagram I drew as desk analysis coordinator and deputy analysis coordinator for 2 years before that. And it has elements like Oracle on the light curve. It's still very directional. It's still got very, very many pieces to it. But all of those pieces are now trying to do even more, and they're trying to combine even more pieces of data. In fact, they're doing exactly what Wade said. They're trying to add multimodal data, galaxy information to get the host properties and the redshifts in this bottom branch, spectra, etc., all in service of trying to do better cosmology. And that gives you the next bottleneck that you have. Rubin's own data does not live in one compute location, let alone all of this ancillary data. So if I want not just Rubin, but the Roman Space Telescope that is launching in August of this year, the Euclid mission, which has been up in space for about 1,000+ days now, and I have to do any kind of compute on them, I have HPC resources. DESC is a DOE funded experiment. We get access to NERSC and Aurora and resources in France and the UK, but I still need to co-locate that data to do any kind of joint pixel processing. And I don't even necessarily have a good way of querying the data from these different catalogs or these different data sets. I can't necessarily always do it on right ascension and declination on the sky because something like a Euclid or Roman, which has 10 times the resolution of Rubin, can take a blurry Rubin source and de-blend it into multiple different sources. So a single object in Rubin can look like multiple different sources in these other surveys. And if I'm a sort of science collaboration that cares about moving object, well, obviously position is a terrible key. So there is no common way of saying this source in this survey is the same as this source in this other survey. That is a honest to goodness computing challenge that we don't have a good solution for. Now, even if I could assemble all of the survey data at one time in one place, realistically, each of these different experiments has a pipeline that's changing every 6 months to a year. The schemas change, release timelines don't align. So how do I actually do provenance with this kind of thing? Right now, just to combine some early LSST data from data preview one, this thing on the left-hand plot at the bottom that says DP1 with DECAM, took individual processing of all of those images of the kind that Shreya mentioned, and then we had to go download all of the Euclid images that happened to be taken at the same time by hand, run all of this processing manually, run the light curves through one AI model, run the host galaxy photometry to a different AI model to get all of this stuff in one place. And how do you scale that to millions and millions of objects? Well, again, I promise I'll try to give you at least partial solutions. So if Desk has part of a pipeline, one thing we can do is split up that pipeline into different pieces. And I think I might have the time for this. So I'm going to waste a second or two to do a live demo. This is all running in NSF Access. This is a service called Blast. And it basically takes a task that's fully pipelined. I'm just going to pick one of these things and hopefully it'll be halfway reasonable. And so what Blast does is retrieve images from different surveys wherever it can. Whatever is currently available, Rubin is currently not available. You can actually see the different resolutions over here. And then tries to do processing to figure out the properties of that source at that location. And even though that is happening in parallel on NSF Access in real time, as long as this web service has a API, ultimately I can go retrieve all of the data for any object and hopefully do my data analysis downstream with something like this API itself. Sometimes the processing status can't ever be finished because something fails in the process itself. And you can see that this is the sort of challenge again with computing that we have. We're trying to run these real-time systems on real data in the cloud, and things simply break. And we're never necessarily going to be sure about exactly why that is. But this is the sort of thing that we'll have to live with. So Blast, when it does work, will produce something like an SED for each of the galaxies that we'll have in Rubin at the location of the center of the galaxy as well as at the location of the transient. Maybe that's a supernova, maybe that's a kilonova, maybe that's a superluminous thing. And so that gives you the sort of multimodal information that you can use to maybe do further downstream tasks. But by atomizing it as a service, you can actually do a little bit more. I don't actually know how to deal with the multi-survey provenance problem. I did introduce that as a bottleneck. And I will say that I think all of the interesting science with Rubin is going to be multi-mission. But our compute model really doesn't understand how to track what data come from where or how. And you can see the value in doing this. So this is two simulated images, Rubin on the right-hand side and the Roman Space Telescope on the left-hand side. And you can see the extra resolution that you get from Roman being in space above the Earth's turbulent atmosphere. And you can see that you want to combine these data sets. It's just a really hard problem. And I think actually the more and more our grad students get used to doing things with agentic AI and vibe coding services that want to kind of combine different data sets and do these multimodal analyses, then we've got this problem, and it's going to become even worse because the AI is certainly not checking if the pipeline version was 1.3 or 1.7. And again, there is no common transient IDE across uh, MAST for NASA or the 9 different Euclid SDCs and for Rubin. So even just cutouts and host galaxy coads for transients in just the overlap region between these three is going to require at least 3 separate queries, and there's no shared key. This is again just a messy computing problem, and I would love to know how people try to solve this for geodata or biology data or any other sort of problem where you've run into this sort of thing, because we don't have great solutions in astronomy. If I focus on the multi-messenger side of where things can go wrong, you saw this beautiful map of the discovery for GW 170817 from Michael in his talk earlier, and you can see that lovely discovery from SWOPE of the electromagnetic counterpart that wasn't in an earlier DLT-40 image. But what you didn't see was the background for how this was actually discovered. You can see these messages on Slack from Charlie Kilpatrick and Ryan Foley and Dave Coulter, literally sharing screenshots to try to coordinate their discovery. Now, that was for the one event that we made happen. And remains like the prototypical example of a kilonova. There might be a few others that people debate about. But you can ask if you can find more of them in the data, and hopefully you don't want to use a Slack messaging methodology to find this or evaluate your pipeline completeness, of course. And that's really hard work to do. So you need to know where your survey pointed. You need to know the localization region. You need to know those EM detections as Shreya was trying to do. You need to know which ones aren't artifacts. You have to be able to report the candidates. You have to get rapid response spectroscopy, and then hopefully get other photometry. And groups like ZTF have tried to do this for a whole bunch of events in O3, including of course Shreya in this 2020 paper, which I think is absolute classic that everybody should read. And the resources to me dedicated to the search was staggering. From just ZTF, there was this 47 square degree camera, but there was also DECCAM, there was the Las Cumbres Observatory. So just a massive amount of work. And they looked at something like 2 million something candidates and then found at the end of that pipeline, after they did all of the vetting, 0 kilonovae. Now, the fundamental issue, like we said, is that kilonovae are faint and fast and incredibly rare, but that is going to create a bottleneck. If we want to coordinate multiple facilities, and I'm going to play this video showing you the problem that you don't coordinate the facilities, you get a whole bunch of overlapping observations over and over again within seconds of each other, essentially, that are wasting data. If you don't coordinate multiple facilities across ground and space, across the EM spectrum in real time, then you effectively have not searched the area as well as you could. So you are very, very likely to miss the kilonovae. And of course, all of this infrastructure that I've showed you, that Shreya showed you, has all been done with offline processing. But we actually have to have all of this infrastructure working in real time when a gravitational wave event actually happens, which means if you're trying to do what Michael showed you for a 30-second odd signal in the gravitational wave, and there's maybe 5 of those in a year or 18 months, then you need basically 24/7 availability of your services with no downtime. That is really hard, and it is worse, very expensive. And I have to unfortunately justify our existence in SIMA to the NSF with these numbers, right? So I'll try to deal with our solutions in reverse order here. My potential solution for trying to get that kind of availability and uptime is to rely on the commercial cloud as far as possible, because I think they have the best availability, scalability, and redundancy there is. And so all of our services in SIMA are built on commercial technologies. We built it on Apache Kafka for the backbone. The entire server is cloud-based in AWS. We have tested it to have less than a second latency through all of Run 04, not just for the external LIGO messages that we process, but also for IGWIN Alert, LIGO's own internal messaging system. So you can do this for your own project. It's not hard to add in a new project into Hopscotch and Simmer. And so we're interested in collaborating with groups like Argus that you heard about earlier. We have all those public topics that you heard about from Shreya. And we, of course, feed all of this into Rubin to trigger Rubin's own target of opportunity. But again, the core issue isn't just that you have the pipes to pull the data that have the availability. The core issue is that you actually have to coordinate the follow-up observations. And so we're building this service called Heroic that gets telemetry data from different telescopes around the world. I'm going to click on the south here because then hopefully you'll actually see some of these things. So this is the Blanco 4-meter dome. It shows you whenever I click on something, the availability of that facility at a given time. And you can enter in a target over here if you like and see what facilities can observe it. You can see what's available at night and so on and so forth. So this is currently being built for Las Cumbres Observatory and the NOAA lab facilities, but we are actually trying to build this to also add in the NASA facilities to keep a track of what satellites are doing at the same time. And hopefully we'll start to add some radio facilities as well in the near future. This is, I think, a hard thing to do, partly because you need to pay for it again for 10 years, but you have to get buy-in from each of the observatories. And in a very real sense, many of the observatories, I think, actually kind of prefer to be siloed. They don't want to have an organization like SIMA, which sort of seems like the UN of astronomy, telling them what to do, or trying to have to work with a different management team and pulling a developer from something that they could do internally to build something that could work across the board. And so this is where, again, it's helpful to have the funding agencies to lean a little bit on facilities, but actually building the system itself is also a computing problem because you are trying to get completely different siloed facilities to work together with high availability, with high reliability. And so if you try to pull hopscotch and this kind of ecosystem into the entire diagram, it stops to look like a directional thing like you had with the brokers and desk, but rather looks like a map with going in every which direction, trying to connect everything to everything else. And that's, again, complexity that is going to be adding to the computational bottlenecks. Each one of these things, as you heard about in the first half of the session from Kelsey, was it, adds a little bit of latency. And then finally, I want to wrap up by talking a little bit about the AI element. I apologize if I can't really see the chat, so I see there's a message there, but I don't know what it says. I think that AI is everywhere right now. Everybody sort of sees it. It is very critical if we're going to be dealing with multi-survey and multimodal data, and it is kind of critical to do things at Rubin's scale. So we've got to feed these AI models with really high throughput and bulk services to do things like BLAST to retrieve postage stamps from different services that had to rely on an underlying service for something like postage stamp retrieval. We have to do really fast catalog cross matching. Again, all of these things can be built. Those are the technical challenges to this problem, but the real computing bottleneck, I think, is actually going to be somewhat different. It's that these models are getting more and more complicated with AI. So if my goal is to combine Rubin and Roman and Euclid, then I don't just care about transient classification and I don't just care about F1 scores. I actually care about inferring the physics of transients. I care about things like forecasting what the behavior is going to do as this model sees more and more data. And this is what we've been doing at the NSF Simons Sky Institute, where I'm the deputy director, is building a foundation model that we can train on the same sort of simulated data sets that Ved and others have talked about, but then we can try to apply it to real data. And the nice thing about this is it's class agnostic. We can do things like forecasting, we can do classification, but we can also do anomaly detection or similarity search all within the same model. So this is the sort of thing that could potentially serve many, many users. And the nice thing about these models, particularly if you use them on big GPUs, is that you can do all of these 4 million elastic simulated alerts that or objects that we have in just a few seconds. It really is a quite night and day thing. But the thing that makes this hard to do is that, again, you have to deploy this model in real time on infrastructure that now needs large amounts of GPU access, and I don't have a great compute model for that. You have all the latency from trying to assemble not just the light curves, but again, the host galaxy data, as you heard about from Ved, that will, of course, add latency into this pipeline. And it is just a lot of work. For one single model, we've had to work with NVIDIA developers to do all of this Triton compilation, to do distributed training. And this is just for one model from one group. So what happens in the near future when every single grad student and postdoc wants to run one of these on their own? I don't know how to give people a whole bunch of warm GPUs that can handle streaming data on demand and build all the services to actually feed these models. Our ability to build complex models is outstripping our ability to deploy them in real time on realistic pipelines because the compute infrastructure I don't think yet exists. So I'm sort of going to wrap this up a little bit and say, I think there's a diverse set of time domain science out there, but that actually means that there is no single compute model. And I think the primary bottleneck that you'll encounter really depends then on the science case. I put in 9 compute bottlenecks that I thought, but I think these are common irrespective of what science you're trying to do. So streaming compute is just a hard issue. Provenance tracking and cross-archive data assembly, again, without any kind of common way of referring to the same object in different surveys, that's a messy compute problem. This real-time optimization, when you have a hard deadline, when you have to trigger follow-up within a few hours before the field sets, and try to do this orchestration across multi facilities that are really kind of siloed, that is again a hard compute problem. And I really do think that we need a new compute model that is not just a whole bunch of here are a whole bunch of nodes on a cluster on some campus. And we really do need to think a little bit about how we are dealing with some kind of fair and equitable access to GPUs in a world where, if you want a 5080 or something like that right now, you're looking at several months of wait time if you can even get it, and several of thousands of dollars. And that's just not feasible for most of us. And we now have to build this competing with the commercial AI space at the same time as Ruben is starting up, and we somehow have to fund this all for 10 years. So I think all of the partial solutions I have are sort of band-aids to get us a few years into Rubin operations. But I don't think they're ultimately problems that astrophysics can solve or should solve. They really are computing problems. If the AI stuff is interesting to you, I'm going to ask you to think about coming down from Madison to Chicago to the John Hancock building where the Sky Institute is. We'll be talking a little bit about a lot of this stuff, in particular how to deploy these models on real Rubin data, how to make best use of them for LVK over there. And I'll stop there and take your questions.
All right, thank you. So we'll ask Nathan to come down and get ready for his talk. Are there any questions for Gautam?
I have a question regarding the key. Why isn't a sky coordinate in time a sufficient key to compare different observatories?
Yeah, I went through that a little bit fast, but the basic issue is that the resolution of these facilities is quite different. You can obviously tell this if you were doing localization with a gravitational wave event and something like an optical counterpart. The gravitational wave sky maps, the median 90% localization area was something like 1900 square degrees. Whereas in the optical, we can give you a position to, better than an arcsecond quite easily. Radio can do even better than that. But the issue, of course, even within just the optical, is if you have a space-based observatory like JWST or Hubble or the Roman Space Telescope, is that they have so much better resolution by virtue of being in space and above the Earth's atmosphere that a single source that looks like a blurry blob in Rubin ends up looking like 4, 5, 6 sources at Rubin depths in these different surveys. So you've got a one-to-many matching problem. And so a single position from Rubin is just not accurate enough to tell you what source you're trying to match against.
All right. Let's thank Gautam again.